So this tutorial is going to cover solutions, which are mixtures, and we're going to deal with problems associated with concentration. Concentrations are basically how strong a mixture is. Anything is strong, like if you're talking about sugar mixed in water, just how sweet is it? The more sweet it is, the more concentrated it would be. And the reason for this is there's a lot of practical situations where we need to know how strong a solution is, how concentrated it is, or how weak it is in practical situations. And so in those cases, we need to actually do calculations so that we know what concentrations we're dealing with. So the first thing we're going to do is define a solution. And that glass of iced tea, for example, is a solution. And basically a solution is a mixture in which the particles actually that you mix different substances, and the particles, they don't chemically react with each other, so they actually remain separate. So if you were to mix salt with water, so again, a solution is a kind of mixture, and the particles are very, very tiny, and they mix very, very evenly, or homogeneous, they call it. So solutions are homogeneous. These are characteristics of what a solution is. And so if you were to take a salt and put it in water, for example, okay. So let's say I have a container with water, pure water, and then I have a pile of salt here. Let's say sodium chloride, okay. And I mix them together. Then the two particles, the water molecules, and the sodium chloride particles are going to mix together very, very evenly to make a solution. And now you have salt water. But the salt doesn't react with the water remains the water, and the salt remains the salt. To where another characteristic is that the particles actually remain physically separated. They don't chemically react, and that means you can separate them by ordinary physical means. So the substances that are mixed can be separated by physical means, not chemical, by physical. Okay. So physical might be like filtering, and the particles are big enough. Here the particles are very tiny, but one way we can separate them is to boil the water. The water boils away, and the salt stays in there. And the water is the water, and the salt is still the salt. They didn't change into something else in the mixture there. So what we have here is when we do put the salt in there, okay, we add the sodium chloride to the water, we're going to get what is called a solution. Okay. So what is a solution? A solution is going to be the water and the sodium chloride. Now the water technically is going to be called a solvent. The solvent is what we're going to put the added substance into to dissolve it. So it's a solvent. These are key terms here. And the sodium chloride in this case would be called the solute. Typically, the solute is going to be what we have lesser an amount of. The solvent is something larger. Now, when the solvent is water, okay, and we dissolve something like sodium chloride, you can put sugar in there, or any other thing that can dissolve in there to make a solution. Whenever it is water is the solvent, then we call them aqueous solutions. So like Aquaman or agua, right? So aqueous. And so oftentimes the most common kind of solutions we deal with are aqueous solutions, right? And within cells, the water is the basis for what you find in cells in your body. Your body is a high percentage of water. So again, what is a solution? A solution is the solute plus the solvent. So it's very important what we're defining. So let's take this iced tea. If we ignore the ice cubes, they're not actually part of the solution. They're separate frozen blocks, cubes of ice. The iced tea there actually has substances that have dissolved from the tea leaves themselves. So let's just ignore that for now and say we haven't added sugar yet. So right now there is a zero sugar in there, but once we start adding sugar in there, it would be a sugar solution plus the tea in there as well. So the tea and sugar combined solution. I'm going to use tea again in some examples, and we're going to ignore the tea and just focus on the sugar there. So we want to make sure we know what these key terms are. a solution, the solvent, and the solute. They're very important as we define concentration. So now we want to look at concentration, and I use the tea for an example. Let's say that you're at a restaurant, they bring iced tea to your table, right? And when they do that, it's not sweet. You're like, I wanted sweet tea, right? So and they only had sugar. They didn't have artificial sweeteners. So you are going to start putting sugar in there you might pour it in there. You might put it by the teaspoon. You might put in one tea, like a scoop it out of a container, and you scoop it in. And let's go with spoons because it'll be easier for this example. The point here is that if I were to define the volume of this glass here of tea, an actual volume measurement in everyday activity here is actual glass. So glass is an actual volume. A glass is actually equal to, I think, 8 ounces, right? And then if we use the spoon, okay, and we put a spoon of sugar in there. So we put 1 spoon of sugar in there, right? Table sugar, which is sucrose. We put 1 spoon in there, and our volume is a glass. Then we actually have a concentration of 1 spoon per glass. That's our concentration. What would happen if I put in 2 spoons, right? And then we would have 2 spoons for that glass. It's now more concentrated. There's more sugar in there, right? And what we're looking at here is a ratio, okay? What was the sugar? When we go back to those terms from over here, what you want to think right now, was the sugar the solute or was it the solvent, right? And then we made the solution, right? So before we put the sugar in there, technically the solvent was the tea, right? The tea water, okay? And then we put the sugar in there. The sugar is the solute. So what we really have here is a ratio in this concentration of the solute, okay? But once you put the solute in there, that tea now, okay, is not just tea anymore, it's tea with sugar, okay? It's your solution. So here is where we don't want to get confused. It's not the solvent, it is the solution. There's a difference. The solution is what you get when you mix the two together, okay? And there is a big technical difference in there. You don't want to make a 1 spoon per glass sugar water, for example, and the first thing you do is fill your water all the way to the top. Fill your glass with water all the way to the top before you put the sugar in there. What's going to happen when you start putting sugar in there? You might go over the glass limit, right? To be clear here, sometimes the particles pack differently, and but as you just think about it, right? We want to have exactly 1 glass, so we need to know what is the final volume going to be when we put both the solute and the solvent together. So there's a difference. So make sure you understand that down here, it's the solution. How do we make it? Well, we had a solvent of water, we put the sugar in there. So be clear on that. So basically, any concentration that we talk about, okay, can be defined as some amount, and there's different ways to measure amount. A spoon, we can measure the amount by mass in other ways. It's going to be some amount of, some way of measuring it, some amount of it, some amount of the solute, sugar, sodium chloride, anything else you're trying to dissolve, divided by the volume of the solution. So let's change that to volume. And there's different ways to measure volume. In science class, we typically measure volume in liters or milliliters and so on. But I'm using glass because we use glass every day. Glass is a volume of 8 ounces. So we would say volume of not the solvent, but the combination. Once you mix them together, the solution. Okay. So if we say so when we start talking about different ways of measuring concentration, they're always going to have this form: the amount of the solute, the ratio of the solute to the solution overall, right? So going back to my example here, we can play around a little bit with this idea with some just general questions, right? The answer is our concentration, okay? So let's say that I give you a solution that has X concentration. Don't know what it is. And I ask you, okay, here's your solution. Okay. Let's say it's this glass of tea. Okay. And I tell you, okay, I have a glass of tea and it has a concentration of 1 spoon per glass of sugar. That's the concentration for sugar for this tea. It's 1 spoon per glass. And I ask you, well, what happens to the concentration of the sugar if I double how much sugar I put in there? What would double mean? Double would mean we're not putting 1 spoon, but instead we put a total of 2 spoons. Okay, so now we've doubled it, right? Okay. So now we don't have 1 spoon, we've doubled 2 spoons. Okay, so I put 2 spoons in there, it's still 1 glass. What's happened to the concentration? I mean, the answer would be, well, it's now 2 spoons per glass, which is twice as much as 1 spoon per glass. So at any time you double the solute, you're going to double the concentration. Okay. What happens if I put 3 spoons instead? Not 1 spoon, not 2, but we put 3 spoons. Then it would be 3 spoons per glass, and we've tripled that concentration. Okay. So another way to look at this would be if I ever give you a question and I say, hey, I don't even know what the concentration is. We're just generalizing. We're just practicing our understanding of the concentrations, right? And I tell you, you're given some solution, concentration X. It could be sugar solution. It could be a salt solution. And at some concentration, I even tell you what the concentration was. There's different ways to measure it. It's just some concentration X. And I said, what happens to the concentration if you double the solute? Your answer would be that it doubles. What happens if you triple it? Your concentration would be tripled. And the way to look at this, we used to always have problems with these kinds of questions, right? They would always ask in concept, what happens to this quantity if you double or triple or do this to this other quantity? The trick here is to say, well, since I don't know what it is, let's just say that the amount of the solute is a value of 1. Okay, so it would be 1 on the top. 1 spoon, 1 gram, 1 kilogram, 1 whatever. And that the volume is 1 also. 1 liter, 1 glass, whatever. We didn't even know what they are. We just say it's a 1, 1. Okay? And 1, 1 is going to be equal to that 1x there. Okay? Now then I ask you, what happens if we double it? What you would do is just multiply by what you're doing. We're doubling. Okay? So if we double the solute, and it was originally 1, what's 2 times 1? The answer becomes 2 on top, and on the bottom it's still 1, so 2 over 1 becomes 2. And that tells us that our new concentration would be twice what it was before. Okay? Let's try that again. Right? What if I were to triple the solute? We would not put a 2 here, we would put a 3 here. Okay? The bottom still stays 1, and we don't know what the real concentration is. Since we don't know, let's put a 1 on the top and 1 on the bottom, and then let's do a little bit of quick mental calculation. If I triple the top, that triples the top here. The bottom is still 1. This means your concentration would be 3 times what it was before we tripled it. Okay? So that's the way you would think about these kinds of problems. Okay? General questions. So that means your the concentration of the tea, if we were to do using spoons, would be 3 times sweeter or 3 times stronger than it was before. Okay. Now, let's ask another question. Let's say I took that iced tea, okay, and let's say we don't know what its concentration is. Okay, I don't even know what it is. We're just starting with iced tea. It's a certain sweetness. It's a certain amount of sweet. Somebody sweetened it. You didn't even know what it was. But here, it's this concentration. Okay. And I took this same tea, and I poured it into a larger glass. And let's say that this glass has a volume twice the size of the other one. Okay. So now when I pour it in there, the tea comes to about right here. It's wider, right? So it's not going to go as high as here. And what I do now is I pour extra water in there to fill it to the top. What I've actually done is something called a dilution. But clearly you can say, I'm not adding more sugar. What's going to happen to the strength of the sweetness or the sugar strength? It's going to decrease. We're actually diluting and decreasing the volume. But what we've done is we didn't change the solute. We're changing the volume of the solution now. Okay? So now in this case, I'm going to be asking, what happens if we double the volume of a solution that was concentration X? Okay, we're going instead, in this case, 1 glass to 2 glasses or some volume, right? I'm not doing anything to the solute this time. We're not adding any sugar or any salt or whatever the solution is. So this stays as a 1, okay? This is understood to be 1 also, but we're not, now we are doubling. So we double the bottom. What's 1 over 2? Well, 1 over 2 means that our new concentration is half. Will be half of what it was. So now it's only half as strong. Okay? What happens if we were to take this and put it into a glass that's 3 times bigger? Instead, that would be 1/3, 1 over 3. Okay? And so that's the way we want to think about these kinds of general questions about solutions. You don't even know what the concentration is, but I ask you, what happens if we were to triple the volume by just adding water to it? Well, what's happening is you're diluting it, and if we were to triple the volume and put it in a glass 3 times bigger, then it would be 1 on top, but on the bottom would be 3, and so now our answer would be 1/3 of what the original concentration would be. Okay, I do ask types of questions like that from time to time just to check to see if generally we understand what happens to solutions when we either add more solute or add more volume to them. So one common way to measure, a rather easy way to measure concentration of solutions in biology is a percent concentration. And there's different kinds. There's solutions where you mix 2 liquids, say ethanol, which is a kind of alcohol, with water. They're both polar and they mix. And if that was the case, then it would be a volume to volume. So like right here, you see mass here. This is when, you remember we were talking about concentration in the prior video, and concentration is the amount of solute per solution, right? This is supposed to be volume of solution, right? But if the solute is a liquid, then it would be volume per volume. But we're just going to deal with percent mass by volume, and we can write down this formula and concept like this. So we're talking about percent concentration, okay, or simply percent mass per volume. Sometimes you see weight per volume, because biologists sometimes use the word weight instead of mass, but your mass is more consistent regardless of where you're at than weight is. Weight is would differ if you went to the moon, for example, but so I'll use mass instead. And so here remember it's an amount of the solute, so in this case it's mass, so it's the mass, and it's going to be mass in grams. And this is of the solute. And this is going to be divided by the volume of not the solvent, but the solution. Okay. And in this case, it's going to be convenient to have that volume in milliliters. Okay. And then you're going to multiply it by 100. Okay. And so the simplest way to think about this is if you were going to make a concentration, a solution of a certain concentration, and you were going to use a 100 milliliters, that would be easy, because when you think about it, if you're going to make it per 100 milliliters, that's percent. Every 100 milliliters cent is related to 100, right, or hundredths. So if we were to do 100, it would be very easy. If I said make a 5% solution in 100 milliliters, is really easy because it would be 5 grams, right? So if our goal was to make a 5% solution of whatever. And the beauty of this, it doesn't matter what the substance is. It could be sodium chloride, sucrose, or whatever. It would be made exactly the same way. A 5% solution would be basically 5 grams in 100 milliliters. When you divide 5 by 100, ignoring the units, you're going to get 0.05. 5 divided by 100 is that, and then you have to multiply by 100, and that gives you the 5, which is the 5%. Okay? And so it would be 5 grams of sodium chloride or 5 grams of sugar in 100 milliliters. It's always convenient that way. Okay? So think about this now. If I asked you, what if I wanted to make a 10% solution of sucrose, which is table sugar, in 100 milliliters? 10% in 100 milliliters, how many grams would that be? Okay. And the answer would be 10 grams, because 10 divided by 100 is 0.1, and then times 100 gives you 10%. So it's very easy when the volume is exactly 100 milliliters. Remember, we're defining it as grams of the mass, which is a mass, grams of the solute, which you're dissolving in there, and milliliters is the key there. So here's a typical problem here. And on the right, these are the tools we actually use, the instruments we use to make very relatively precise concentrations. These are called volumetric flasks. They're a bit expensive. And you can see on the top, they have a container up there. And they're all labeled with the volume that they're used to make. So this largest one is 1,000 milliliters or a liter. This second largest one is 250. There's 500 ones too. They're just not in the picture. This one is 100 milliliters, and this one is either 75 or 50. But you can see they have a narrow neck there, and they have a mark right there on the neck. And the idea here is when you're done making your solution, if you're going to get exactly 1,000 milliliters or 250, whatever you're looking at, you're going to put a certain amount of water. You don't want to fill it all the way up yet, just like with the iced tea example in the last tutorial video. You're going to put a certain amount of water. Then you're going to put whatever it is you're going to dissolve in there, whatever solute, whether it's salt or sugar or whatever you're mixing in there. Put it in there, and then you grab the flask from the top there and you just swirl it around, and you're swirling it around. You're trying to dissolve as much, if not all, of the solute in that water. Then once you do that, then you fill the remainder with water right up to that line there, and then you cap it on the top, and then you just invert it back and forth. And what you've done is you've created 1,000 milliliters of that solution. You would do the same thing if you're trying to make a smaller amount, 250 milliliters or so. You just pick a different size volume flask. Now remember, I said earlier that if it's 100 milliliters, it's very easy. You can just think about it. If you wanted to make a 15% solution, 100 milliliters of 15%, then it's 15 grams. 15 grams out of 100 gives you that 15%. But I've given a problem where we're actually going to have to use the equation here. And why is that the case? Because we don't have exactly 100 milliliters. We have 250 milliliters. So let's look at our equation here. We know this is going to be a percent concentration. They didn't even tell you what the substance is, because it would be the same mass you would need regardless if it's sugar or sodium chloride or potassium chloride or whatever other substance you're trying to mix in there. It could be citric acid, anything you're putting there would be that mass for that volume. So we're talking about a percent mass per volume. This is our concept equation. I always tell my students, what we got to do is use the formula, write it down so you can see it, okay? And I'm going to just shorthand here, and just to say mass, and we understand that this is going to be the mass of the solute, okay? And then this is the volume, and what we want to do is remember that it's volume in milliliters when we're talking about percent concentration. So it's mass in grams and volume in milliliters, okay? Now we want to go here and see, well, what do we have? What's given in the problem? And here's where you got to know your units. We got to know what milliliters are, because this problem doesn't tell you what it is, but I know milliliters is a volume. And so you always want to identify your knowns and what is the unknown. Just like we had to solve word problems in classes we've had before. Okay? You write down everything you have. I know I have 250. And the reason why I know it's a volume is because the units. We know the units. That was covered in the metric system. There were units that I wanted you to know. Okay, so you have to be able to identify these so that you know that you can use the formula. Okay. Now, what is 5%? 5% is given to us, but what is that? When we look at this formula here, it's not mass, it's not volume, it's this. So this is our percent mass per volume. Okay, that was given there. And we're asking, it asks how many grams. They could have asked what is the mass, right? Because what mass of substance X is the same as saying how many grams. So our unknown here is mass. Okay? So when we look at this formula here, the original equation, we can either rearrange it and solve for what we're looking for. In this case, we're looking for mass, or you can plug in the numbers, which I think some students find it easier to do rather than trying to move letters around. So what I'm going to do is I'm going to go ahead and plug in. I'm going to use this equation as my guide, and I know that the 5 goes on this side here. So it's going to be 5, and you can leave out the percent if you want. Okay. On the right side of the equation, we don't know mass, so we're going to put M there. On the bottom, we're going to substitute our volume, 250 milliliters, and then we still need the times 100, okay? So now all you got to do is solve for M, and what we got to do is we got to isolate M, get it by itself. So whatever's being done to M, we have to do the opposite. So 2M, we're dividing by 250, and we're multiplying by 100. So I'm going to start by getting rid of the 100. If we are going to multiply by 100 to cancel it out, you're going to divide by 100 or multiply by its reciprocal. Okay. So that cancels. Okay. This, and then you write down what you have left over. We have on the right side 200 M over 250 milliliters. And then over here, 5 times 1 over 100. This is kind of like saying 5 over 1. So what this gives me is 5 over 100. And if you did that calculation, it would give you 0.05 as your answer. You can do that now or do it later with your calculator. And so the next thing I got to do is multiply both sides by 250 to cancel that out. You remember any number over 1 is the same as that number. So 5 is the same as 5 over 1. It's the same thing. So this is kind of understood to be over 1, and that means if they're on opposite sides, we cancel. Okay. Well, all we have left now is our mass. Okay. And so now all we got to do is this is over 1, and we're going to multiply 250 times 5 and then divide by 100. We don't have to divide by 1 because it gives the same, right? So 250 times 5. I think that's going to be 4 would be 1,000, so there's going to be 1,250, and then we're going to divide by 100. You use your calculator, right? And then you divide by 100, and the mass that we need to add there is going to be equal to 12.5, and we know mass has to be in grams. Okay, so how would you make this solution here? And I do have a calculator, so if I got a calculator, and on quizzes and tests, you'll have the calculator activated on your the web browser, your lockdown browser. 250 times 5 divided by 100, and it gives me 12.5. That's good. So now in practice, we know how many grams do we need to put, and we need a volume of 250. So that means if I'm going to make this solution, I wanted to make 250 at 5%, and it doesn't matter if this is glucose, sucrose, table salt, magnesium sulfate, doesn't matter. What you're going to do is you're going to weigh out to get that 5%. You're going to get a mass of 12.5 grams of that substance. That's why I put X, because it doesn't matter what the substance is done the same way, regardless. Okay, so a 5% solution at 250 milliliters, we would want to use this flask here because it's the 250 one. We're going to put water part of the way, maybe about halfway on the bottom part of the flask. Okay. Then we're going to take the 12.5 grams of that substance and put it in there. And then you mix it around. You might close the top to keep any from splashing out. You mix it around until that substance dissolves. Then you open the top, and then you're going to put water in there. Okay. And you're going to fill it up to that line right there, exactly to that line. close it up, and then just invert it to mix it. And what you have now is 5% solution of whatever substance that is. So that's how, in practice, we would make a percent concentration solution. So here are some questions you might want to consider. You can press pause on there. This is what you could work as a little bit of practice. So here I actually give you, in this one here, is how many grams of sodium chloride would be needed to make 200 milliliters, so not even a 250 milliliters at 5%. And remember, it doesn't matter what the substance is. This could have been X, right? You're basically looking for a mass there. Okay. Another question you might consider, and it's the same question. I just asked it very long way and then a short way of answering it. At the very beginning, in the prior segment on concentrations, that I talked about how you can think about solutions. And so this one's asking, what happens to the concentration of any solution, whatever it is, if you took that solution and poured it into another container that was twice the volume, and then added enough water to fill the container? This sounds like we're diluting it, right? It's going to become less strong. Okay. So basically, what am I asking? Basically, what happens if you double the volume of the solution by adding water only? You're not adding anything else to it. Okay, so those are some items to consider. In your lab manual, there's going to be some percent concentration problems that you've been asked to do for practice. Okay. So it turns out when we're dealing with concentrations that percent concentrations are quite convenient to make. They're relatively easy to make. You just need to mass or weigh out a certain mass and put it in a certain volume, and that's relatively easy. The problem with this is that a percent concentration solution can be deficient when we need to actually know how many molecules of solute are in there. And oftentimes that's very important. Knowing how many particles, molecules, or ions that are dissolved in a solution are important in determining osmosis, which is the movement of water across membranes. That's important. It's also quite important in determining when, how fast, and in what direction chemical reactions would occur by certain concentrations of these particles. So in chemistry in general and in the chemistry of life, sometimes we need to know how many particles there are, and percent concentration fails us. And let me show you what I mean with an example that we might be able to relate more. Let's say we had some coins, kind of like a penny or a dime and a quarter or something like that. We have a small coin. These are made up coins, right? But it's kind of fun to play around with money. This could be like a penny or a quarter, a dime or whatever. They're hypothetical coins A and B. And coin A has a mass of 1 gram, and coin 2 has a mass of 2 grams. This is much lighter than probably what a quarter would be, right? But we're going to pretend. And so let's pretend like we can take these coins and make a pretend solution that we can dissolve them in exactly 100 milliliters to make it very easy, right? Because remember, we're making a percent concentration in 100 milliliters. Whatever that percent is, we just get that mass in grams and put it in there, right? So let's say that I wanted to make a 10% solution of coin A in there. Let's just pretend we can dissolve them in there, and then if we evaporated the water, the coins would come back. Okay, so we can dissolve in there, just to make the point. So we have a 10% solution of A and a 10% solution of B. Quick mental calculation, because it's in exactly 100 milliliters. That means we would need to get 10 grams of A and put it in there to 100 milliliters. We would also need to have 10 grams of B. But now I want you to think about the mass of those coins. If we make a 10% solution of A and a 10% solution of B, and we think about what the masses are, right? Both are going to require us to put 10 grams of A in there and 10 grams of B. I'm going to ask now, is each solution A and solution B, are they going to have the same number of coins in there? Same number of particles, right? Each coin is a particle or a piece. And the answer should be no, because if we actually went there, if each coin is a gram and we're going to need 10 grams to make 10%, then we would need we would have 10 coins in solution A because that coin is smaller. And when the particle is bigger, 10% is going to give us less particles. If each coin is 2 grams and we needed 10 grams of it, we're only going to have 5 coins. So while both are 10% concentration, 10% actually means different number of particles for each one. And so that's not going to be convenient when we need to keep track of number of particles. Okay, so the same thing goes for if we wanted to make, and this is a real good example here. If we looked at glucose, a glucose molecule, on its own has a mass of about 180 atomic mass units, the mass of one molecule of glucose. Sucrose, which is a disaccharide, something you're covering in lecture this week, or we may have already covered it. Sucrose is a disaccharide made of basically 2 6-carbon sugar molecules. It should be roughly about twice that weight. It's almost twice the weight. Remember, when you put 2 things together, you lose a water dehydration. So you're losing 18 atomic mass units because water is about 18. It's about 18 atomic mass units. So sucrose is almost twice as much. It's about 342 atomic mass units. So if I were to make a 10% solution of glucose and a 10% solution of sucrose, the glucose is going to have more glucose molecules than the sucrose would. They would both be 10% because we're putting 10 grams of each in there, but just like the coins, one coin was bigger than the other one. Here, sucrose is much bigger. So 10% of sucrose is going to give you less, almost half as many particles as a 10% of glucose. And that's not going to work in some situations where we need to know the number of particles. So we need a way of counting particles. When I say particles, I'm talking about molecules or ions, positive or negatively charged particles when they're in that solution. So I want us to think about something we do know. There's a counting unit called a dozen. Okay? We know that 1 dozen is equal to 12. Okay? Now, when the particles are really tiny, it's often convenient that we count with mass instead of counting them one at a time. Like when you go to the store and you buy beans, like pinto beans, you don't go counting them one at a time. You go and you scoop them up and then you put them on a weighing scale and then you get a pound or whatever, right? And that gives you a certain amount of beans. It's the same thing in chemistry. We're going to use masses, right? And so very quickly we start to think, well, if we had a dozen sucrose molecules, right, that's going to be more than what a dozen sucrose molecules would be. They're going to have different masses, but there's a certain mass connected to that dozen, right? So let's say if we had a dozen coin A's, then that means the dozen mass for A. So let's call that a dozen mass. The dozen mass for coin A would be equal to 12 grams. So the dozen mass for A is 12 grams. If we had a dozen mass for B, 12 times 2, that would be 24 grams. So it would be per dozen, per counting unit, per dozen. Okay. These would be the dozen masses. So there's a certain mass for it. So if I gave you 12 grams of coin A, you would have a dozen of them, right? So if I gave you 24 grams of coin B, you would have 12 coins, right? Because the dozen mass, which is how many a dozen is 24 grams. If I only gave you 12 grams of coin B, then you would only have half a dozen, right? So dozen can be used for counting in every ordinary odds. Dozen donuts has a different mass than a dozen eggs, right? But in chemistry, we use a counting unit called a mole, and that's related to molarity. So we're going to be looking at, for molarity, we're going to be looking at number of particles as the amount of the solute, and then divide that by the volume. And so we got to introduce the mole. And the mole is going to be a counting unit, and the mole was something that was introduced back in chapter 1. If you watched that lecture, we went through that. The mole is a counting unit, and I know because I used to teach chemistry at the high school level. We had a mole day, and that mole day was on October 23rd, because October is the 10th month of the year, and the 23rd is like the exponent. But the actual number is 6.02, and then it's times 10 to the 23, and that's a real big number. It's like a billion times a billion. That's 10 to the 18, and then times 100,000 times 10 to the 5. It's a huge, huge number. And then you still have to take that one with 23 zeros and multiply it by 6.02. The mole is going to be approximately equal to that many particles. Remember, these particles are very tiny, like an atom or a molecule. Okay. So in practice, though, we don't really actually talk about the number of particles, but it's the same thing. Like if I give you a dozen, you have an idea that I have 12, right? If you have 2 dozen, then you have twice that amount. You're basically counting by every dozen. Same thing here. If I give you a mole of carbon, okay, you have a certain amount of particles. If I give you 2 moles, you know you have twice. So we count by the mole, not really by the particle, right? It's just theoretically, it's a large number of particles. Just like a dozen is 12, a mole in chemistry is a real big number because the particles are smaller. And it turns out that there is a mass-mole relationship. Your 10th grade chemistry teacher probably had you do mass-mole conversions, okay? So this brings us back then. If we know the number of moles, like you know the number of donuts or whatever, the dozens or whatever, but if we know the number of moles of a substance, then molarity, which is going to be capital M for molarity, is going to be equal to the number of moles of the solute, which will give us the number of particles. And then that's going to be divided by the volume, and that volume has to be in liters. This is very important, okay? That if you're given a situation where you're dealing with milliliters, just like those volumetric flats in the last section on this concentration, they're in milliliters. We got to keep in mind that we have to convert the volume to liters before we do this. Okay. Now, this big M is much different than the little m. Okay, so we want to define some things here. Big M is going to be equal to molarity. Okay, and the units are going to be moles, and for the top part, and the bottom is going to be liters. And so that means the units are going to be moles per liter, MOL. Okay, let me rewrite that. The units for molarity are moles of the substance solute per liter of solution. Okay, this is different than little m. Little m is defined as mass. Now that's not part of this equation, but it's going to become important later. N is going to stand for the number of moles. Okay, and V is going to be for molarity, is going to be not volume in milliliters, but volume in liters. So that's something to remember, because percent concentration, it was volume in milliliters. Okay. And another important variable we might need for some problems is MW, which stands for the molecular, which is the molecule. I just lost my spelling. Molecular, the molecular weight. And basically, it's the mass of one molecule of that substance, okay? And so we're going to need these items here. So if I were to use these symbols for these quantities here, then we can write the molarity equation as big M for molarity. The number of moles is N for number, right? And then big V for volume, and we just got to remember that that is volume in liters. Okay, so first things first, we got to be able to figure out, when we're going to do these types of concentrations and work with molarities instead of percent concentrations, we need to know how to calculate the molecular weight of substances, and that's going to require a periodic table. Okay, so remember molecular weight. Molecular weight was one of those important ones here. Okay, so in order to do molecular weights, you need to know the formula. Now, sometimes I'll give the molecular weight, and in practice, the chemist is not calculating molecular weights all the time. When they are working with compounds, the bottles that the compounds come in will have the molecular weight listed on there, or they have a reference guide. They have these material safety sheets that we have in the laboratory, and in there they have the molecular weights for those substances. You just look it up quite quickly. But in case you don't, if you have the formula here for the substance, you can use your periodic table to calculate it. You remember in chapter 2 from the lecture, when we looked at the periodic table, each box has the atomic number, the atomic symbol, and it has the atomic weight, which is the average weight for the atoms of that element. So we're going to use that. So here we're asking for us to calculate the molecular weight of carbonic acid. And this is the formula for it, H2CO3. Now the best way to do that is to make sure that you keep track of how many of each type of atom you have. Remember, you're doing this calculation for one molecule, okay? And so I'm going to go ahead and write down, because the formula is H2CO3, the subscript tells you how many atoms of the element you have. So the subscript for hydrogen is 2, that means I have 2. So I'm going to put a 2 there. For carbon, it's 1, and for oxygen, we have 3 oxygen atoms in that one molecule. Now we need to multiply by the weight of the average weight of those atoms that you get from the periodic table. So for hydrogen, if we look up close there, it'll say 1.01, okay? So I'm going to put here 1.01, and it's technically atomic mass units because it's the average mass of the atom. For carbon, sometimes we see that so often in biology that carbon, we start to remember that's 12.01, okay? About 12 atomic mass units. And then for oxygen, if we keep a lot of decimal places, like 15.99, I've used it so much, I remember it. But if we round it to only 2 places, it comes out to 16.00. You can see that right there toward the top right for oxygen. So that would be 16.00. And now what we do is multiply. 2 times 1.01 is going to be 2.02, and 1 times 12.01 is 12.01. And then 16 times 3, 6, 12, 18, carry the 1, 48, right? So then what you do is you add up everything there, okay? So sometimes that calculator will be handy. I'll have a calculator for you there on the web browser, the lockdown browser. And this comes out to 62.03. So that would be the molecular weight, the weight of one molecule, that would be 62. Yeah, that makes sense. And technically, the units are atomic mass units, okay? So that's the molecular weight, okay? So what is the big deal here? Why do we need to do this? Because it turns out there's a relationship between the weight of a molecule and the mole, okay? So while the weight of this molecule, the same goes for the atoms, like the weight of one atom is 12 atomic mass units for carbon, right, over here when we're dealing with carbon. But the weight of one molecule of this is 62.02 of carbonic acid, and its atomic mass units. So this is the molecular weight. But if I ask you, okay, how does that relate to the mass of 1 mole, which we're going to call molar mass? Okay, this is an important definition. It turns out that the mass of 1 mole of any substance is going to be equal to its molecular weight in grams, okay? So if the molecular weight of carbonic acid is 62.03 atomic mass units, then the molar mass is going to be, we just put the same numbers, but we put grams. And if you get 62.03 grams, because in the lab we can measure grams with a balance, we don't have instrument to measure individual molecules. If we were to measure out that same value there, then that gives us what the mass of 1 mole is. So the molar mass for carbonic acid would be 62.03 grams per mole. If I wanted to know what the mass of 1 mole, remember the mole is that 6.02 times 10 to the 23rd particles. If I wanted to know what the mass of 1 mole of carbon is just the carbon atom itself, then I would need 12 grams. 12 grams of carbon, and that would give me a mole of carbon. If I gave you 6 grams of carbon, I'm just rounding to the nearest atomic mass unit. If I gave you 6, now you have half a mole. If I gave you 24 grams of carbon, now you have 2 moles. So we can count by mass if we know the molar mass. Same idea here. If we wanted to know, if I wanted to give you a mole of carbonic acid, what do I need to do? I need to give you 62.03 grams. If I wanted half a mole, I would give you half of that. Figuring that out real quick here, I need to give about 31.02 grams or so. If I wanted 2 moles of carbonic acid, then I would double that. So whatever twice that, and that would give me 2 moles. Okay. So that brings us to, well, how can you figure out how many moles? Because if we go back to our equation for molarity, N is number of moles, not the, this is volume in liters. N is not mass, it's the number of moles. So in the lab, what we need is a balance to measure out a certain amount to get a certain number of moles, right? But there's a relationship between the mass and the number of moles. It's the molar mass, okay? So here we have another way of looking at it. Here is the formula for glucose. And this is a mass for glucose. And if we're dealing with molarity, there's no mass in there. This big M is not mass, this is molar mass. But it turns out that when we're dealing with this, we need to figure out what the molarity, the number of moles is, right? So there is an actual relationship for the number of moles. Okay? The number of moles is going to be equal to the mass of the substance you're talking about, in this case glucose, and that would be the mass of your sample. And all we got to do is divide by its molecular weight. We just finished learning how to calculate molecular weight in the prior slide, right? So a lot of times I'll give you the molecular weight. If I didn't, like in this problem, you would need the periodic table to figure that out, okay? It's going to be the same thing. In glucose, we have 6. You got to look at the subscripts there. We have 6 carbons. For hydrogen, we have 12 hydrogens. And for oxygen, we have 6. Now, from the prior slide, from the periodic table was equal to 12.01. So you look this up on the table. Hydrogen was 1.01 and oxygen was 16.00. Okay. And so we got to figure out what the molecular weight is because we're being asked how many moles. And we're going to use this equation. So you're going to add this concept equation because it's related to molarity. How is it related? The N right there is the same as that N. Okay. So 16 times 6 is going to be 96. And then 12 times 1 is going to be about 12 if we round to the nearest. Now in chemistry, they really wanted you to keep track of significant figures. Here I'm okay if you round up a little bit. 6 times 12 is going to be about 72. 72. And boy, that's like 6 times 12, right? So, and 0.06. And now we got to do is add them all up, and you're going to get approximately about 180. And that would be the molecular weight, right? Okay. And so, the molecular weight is if we wanted to know how many moles, right, then we would change that to grams, and it would be grams per mole. So in this problem here, we figured out the molecular weight. This is the concept formula to solve this. And so what's given in this problem here? Well, they give us grams, so that's mass, 60.0 grams. Remember, it's always helpful to write down what's been given. You recognize grams as a mass. They're asking us for a number of moles, N. That's the unknown. And sometimes in these concept problems, things are understood. What's understood? If we're given this problem here, we can figure out that other thing, the molecular weight, and we just did. Using a periodic table, that would be 180 grams. Okay. So now we go and we use this formula here, where N is equal to, the number of moles equal to the mass of how much you have divided by the molecular weight of that stuff you have. right? That substance. And so in this case here, we don't need to rearrange the formula. It's already solved for N. So I'm just going to plug in 60. Remember, 1 mole is 180 grams and we have less. So this is going to give us a value less than 1 mole. You can have less than a mole. And so you would take 60 and you divide by 180. And that's going to give you 0.33333. There are rounding rules technically, but go ahead and round to at least 2 places past the decimal here. And so what we have here is the molecular weight is actually going to be shifted to, you get the molecular weight and then you're actually going to plug in the molar mass. So the molar mass would be grams per mole, and those cancel and you get units of moles here. Okay. You're looking for moles, the unit should be moles. Okay. So remember, molecular weight is atomic mass units, and molecular weight, when we plug it in there, we're going to actually put the molar mass instead, but we just want to remind ourselves we have to calculate the molecular weight first. So the molar mass, remember, is the same number, but in grams per mole. When we plug that in there, that does cancel out the grams and give us moles, which flips to the top. Okay, so in order to figure out molarity in the lab, you have a lab balance that measures in grams. So this equation right here becomes important. Okay. So here is a molarity question. Again, it's always helpful to read and identify the knowns and the unknowns and write down anything else that's understood. And in these problems here, molecular weight is understood that you can either look it up on the bottle, or if you have a periodic table, you can figure it out if they give you the chemical formula. And they have here, this is potassium chloride, KCl. Now it says, what is the molarity of potassium chloride solution if 6 moles of potassium chloride is dissolved in enough water to make 500 milliliters of potassium chloride? So remember, you're going to put 6 moles in there. They're giving you the moles already. They didn't give you mass. They're giving you the moles already, and we're going to put it in not 1 liter, but 500 milliliters. Remember the definition for molarity. This is the concept. I already know the concept because they're asking for molarity. It's the number of moles, and it has to be volume, and we remember it has to be in liters. So that means we need to change that to liters. Okay, that got to be a conversion. Now let's take a look at what's given here. They give us this unit MOL as moles, so that means they've given us N. And I found, guys, is that if I stop writing down what's given, and it always helps that you can identify the variable. Mole stands for molarity, which is symbolized as N. If we have trouble writing these down because we don't recognize units, you're going to have trouble figuring out what equation to use, right? The equation is a concept. So you want to make sure you remember the units. Milliliters is volume. Remember, we're going to have to change milliliters to liters because by definition it's moles per liter. Okay, and we're being asked to find molarity. This is the easiest molarity problem you can get because they gave you moles, they gave you volume, and you're looking for big M molarity. And those are all the things you need with this equation. So we have everything we need here. And in fact, we don't even have to manipulate or change it around. So we can just go ahead and substitute into the equation. The top is going to be 6.0 moles. The bottom, we cannot just plug in 500 milliliters. Okay. Anytime you got 500 milliliters, we go to that unit conversion skill that was covered in the metric system lab in week 1. We put milliliters on the bottom and liters on the top. We put the 1 where the prefix is, and on the other side we put what the prefix means. Remember, King Henry died by drinking chocolate milk. You start with 1,000 for kilo and you work your way down, and when you do, you end up getting 0.001. Milli means 1/1000th of whatever it is. In this case, a milliliter would be 1,000th of a liter. So this 1 milliliter is 1,000th of a liter. It's 1,000th of a liter. The liters cancel. And basically, you're multiplying by 0.001, which is going to move the decimal 1, 2, 3 to the left. So this is going to be equal to, that's going to be the same thing as 0.500 liters. Okay, so this is the same as 0.500 liters, and that's what you actually plug in here. If you plug in 500, you're going to get the wrong answer. It has to be in liters. So the answer here is going to be moles per liter, because nothing cancels there. And when you divide by 0.5, it basically is multiplying by 2. So the answer is going to be 12.0 moles per liter. And sometimes the moles per liter, they'll abbreviate with a big M, and that's different than the variable M. Okay, so you see big M here, and then on chemistry, we write what the substance is. So the molarity is 12.0 molar, or moles per liter, calcium chloride. Okay, and that would be your answer there. So here is a different kind of problem, and it's still using potassium chloride. Okay, and this one is more related to the ones that are in the lab manual that you've been asked to practice. And this one is more like what a biologist or a chemist. In biology, we have to make solutions sometimes to do laboratory work. This one is more like what we would use in practice, because we have a balance. And in that balance, we have to measure out a certain amount of grams. So when we say how many grams, we're talking about the mass. Okay, and this one is asking for how many grams. Okay, so that's mass, little m, not big M. Okay, so it's asking for how many grams of potassium chloride to give us the formula. So that tells me if I need to, I can calculate the molecular weight with the periodic table. Okay. Then it says how many grams would it take to be dissolved? Would you need to dissolve in water to make 200 milliliters? So they're giving us a volume there. Okay. And we're going to be making a 1.5. Big M stands for molarity. And remember that is actually shorthand for moles per liter. And they give us that 1. So this is a different kind of problem. In the prior one, we were trying to find molarity. Here they gave it to us already. And that's really what we do in the lab. I need a 1.5 molar solution of KCl. And you got to make it. Well, how are you going to make it? You got to mass out the right number of moles for the right volume. Okay, so this is molar potassium chloride, and we might rewrite it as the big M stands for moles per liter of potassium chloride. Okay. And when I look here, this is our unknown, the grams, our volume, we wrote that down, and our molarity is like, great. All right, I know this is a molarity problem. So we start thinking, okay, that means this is the concept. Those equations are concepts. It's a formal concept that involves math. And we remember that it is the number of moles for the amount of volume in liters. And so when I look here, I said, well, look, they give me big M. I have that one. They give me volume. Yep, great. But it's not asking for number of moles. It's asking for grams. And so we're like, we cannot use this equation. It does not give us what we're being asked for. And so we start to think, well, what can we do? I'm a kid. I'm a biologist. I need to make the solution. I cannot use that formula. We got to remember that second formula I gave just a while ago. The one that has an N just like that, and it's the same N. It's the number of moles. And that's going to be equal to the mass of the substance over the molecular weight, and the molecular weight needs to be in grams per mole. The molecular weight technically is one particle, but we're actually really technically putting the molar mass in there. Okay. So now if I look here, I say, hey, look, that one has what I'm looking for. I'm looking for mass. Okay, so maybe I can use this equation right here to help give me mass. And then this one has the relationship for molarity. So it's really going to be a two-step problem that you have to solve. Okay, so we're going to think about it here. They gave us potassium chloride, okay, and that means we can actually find the molecular weight for it if we have the periodic table. Sometimes I'll give this to you to save you time. But let's go ahead and take a look real quick what potassium and chlorine are. So potassium has a weight of about 39. I'm just going to round it, so I need to write that down. I'm going to forget. For convenience, I'm just going to round and not keep the decimals. So potassium is about 39 grams per mole. And chlorine is 35.5 0.45. It's about 35 grams. Okay. And so now I come back over here and I can actually figure out the molecular weight, because for the formula, it's like we did in the very first problem for molarity, we only have one potassium. There's no subscripts. It's understood to be 1. It's understood to be 1, and this is understood to be 1 for chlorine. So for chlorine, so really, we don't have to do any multiplying. We just got to add up the masses. So I wrote down here that potassium is 39 atomic mass units for each atom, and then chlorine is about 35. And times 1 is just, this is going to be 39, and this is going to be 35. And so then we add those, and that gives you about 74. So this is going to be 74, and we want to use, instead of atomic mass units, we're going to use grams per mole, because it's going to be really the molecular weight, but in grams per mole for this. Okay, so now I have this information here, and I'm going to need to do this thing in probably 2 steps. So what I want to do now is think about how I might use this equation here. So let's take a look here. Like if I take what's given and I look at this first equation here, and then I say over here, this one is where the real deal is, because I'm being asked to find mass, so I'm going to need this equation at some point. But do I have, this is the importance of writing down the things you have. So you got to ask yourself, do I have enough right here to actually find the mass right away? And so what would you need? Well, you cannot have 2 unknowns in a problem. Do we have the number of moles? And when I look, they did not give us the number of moles. So I don't have that one, and that means I have 2 that I don't know. So we cannot use this equation first. Okay. I do have molecular weight. We just figured that out. So now I'm going to go to this first equation because they're related. That n is the same n. Okay, same value. And I look over here and say, well, maybe if I can find n, because n I didn't know, but maybe I can use this to find n. And once I find n, then plug it in here and then use that equation. And let's see if I can do that. Am I given big M, molarity? Yes, it's 1.5. Are we given volume? Yes, but remember it has to be in liters, right? So remember that conversion earlier we did milliliters here, liters here, 1.001. Basically, when you're doing milliliters to liters, it moves the decimal place 3 times to the left. So it's going to be 0.200 liters. And so what I can do now is I can use this equation, and I'm going to use that right here. I'm going to plug in 1.5, and I'm going to use the units moles per liter. And that's going to be equal to n, because we got to look for n so that we can use it in this other equation. I'm going to divide by the volume, which is 0.200 liters. And now what I need to do is solve for n. And since to n I'm dividing by 0.2 liters, I'm going to multiply both sides by 0.200 liters. That will cancel there, but I also need to multiply this side by 0.200 liters. The liters cancels, and that's going to give me a number of moles. So it's 1.5 times 0.2. And that gives 0.3, and the units are going to be moles. Okay. So now, let me double check my calculation. Yeah, and it's like 2 times 15 is 30, but the decimal moves, right? So now I have n. Now I have n, and I can plug in there. Okay. And so now I'm going to take this, and I'm going to substitute that in to that part of the equation there. Okay, so now using this equation here, I'm going to say 0.3 moles is equal to, and we're trying to find mass. That mass was the unknown. We figured out the molecular weight for potassium chloride. That goes on the bottom. So that's going to be 74 grams per mole. And up here is the mass. And that mass is the mass of the potassium chloride we would need. Okay. So I've got to cancel out 74, move it to the other side. So I'm going to move 74 grams per mole That's going to cancel, and I have to multiply the other side by 74 grams per mole. And this would give me my mass. The moles cancel and gives me grams. And 74 times 0.3 is going to equal to 22.2 grams. The moles canceled out. So if I'm going to make 200 milliliters of 1.5 molar potassium chloride, how many grams of potassium chloride do I need? I'm going to need 22.2 grams. I'm going to put it in a volumetric flask that is marked to 200 milliliters. I'm going to put that in there, dissolve it in a little bit of water, and then once it dissolves, then pour it up to the 200 milliliter mark, and I have a 1.5 molar solution. Okay. There is an easier way, and I'm going to record a final segment to show you how to do this a lot quicker by combining these two equations. So in the last segment, which was a little bit lengthy on molarity, I promised a shortcut for this kind of problem. In practice, a lot of times we need to figure out what the mass is that we need to make a certain molarity or concentration in moles per liter of a solution. It turns out that we can do this calculation very, very quickly if we just combine the two equations, okay? And the way we combine them here is we're just going to take, because n is supposed to be the same number. If we were to know mass and molecular weight, there's a number there, and that number is equal to n. So all I have to do is take this number, which is right now the variables, and then plug it in and substitute it for the number of moles there in that equation. And if I do that, keep in mind that this is supposed to be a number, but we don't know the number right now, but the number of moles is equal to mass over molecular weight. I'm just going to rewrite this first equation with, instead of n, I'm going to rewrite it with mass over molecular weight. So let's go ahead and write that down real quick over here. Molarity is equal to, instead of n, we're going to substitute what n is equal to. So I'm going to write that down as mass over divided by the molecular weight. Okay, and then, so that was substituted there on the top. And then I'm going to put that line there. I'm going to make it bigger, a little bit longer. And then underneath is the volume. Okay. So now all I have to do is rearrange this equation, and I can figure out the mass right away. Now let's take a look. If I go back to what was given or understood earlier, we had mass. That was the unknown. That's our unknown. We weren't given the molecular weight, but a lot of times it's given to us, or we can calculate with the periodic table. So we have that one. We have V and we have M. We have everything we need now to solve it in one step. So what I'm going to do is I'm going to rearrange this equation to give you the shortcut equation. I'm going to get rid of the V first. So if I'm dividing by volume, I'm going to have to multiply both sides by the volume. Okay. That's going to give me now the mass, what's left on the right, divided by the molecular weight in grams. And then on this side, I have the molarity, not mass, but big M times V. The last step here is I got to isolate mass, because that's what we're looking for. That was our unknown up here. So I'm going to multiply both sides by whatever the molecular weight is. And that cancels, and there's your one equation that's going to solve it for us. So we take the molecular weight, multiply it by the volume and by the molarity, that would give us the mass we need to make the solution. Let's see if that works. Let's see if we get the same answer here. So mass is going to be equal to the molecular weight times the volume of the solution we want to make times the molarity of the solution we want to make. Let's substitute in. Remember, we have to know the molecular weight for the substance, right? That's important. So this is going to be 74, we have to figure that out with the periodic table, grams per mole. We're going to multiply that by the volume. It has to be in liters. We had to figure it out. That's 0.200 liters. And then we're going to multiply that by the molarity, which is 1.5. And we're going to want to use moles per liter instead of big M. That way units cancel when they're supposed to. And canceling the units helps us check that we set up everything right. So here we have moles over liters, but over here we have liters. The liters cancels. Okay, that leaves us with moles. The other one has grams per mole. Since moles is on the bottom and over here moles is on the top, the moles cancel. And if we look, all that's left is grams. And that's good because we're trying to find mass. So the setup is right because the units work out. So now let's just go and crunch the numbers real quick and see if we get the same answer we got the hard way, right? 7 times 0.2 times 1.5, and I get the same answer, 22.2, okay? Which is what we figured out earlier. 22.2 grams, you mix in 200 milliliters, and that will give you 1.5 molar potassium chloride solution. So there's your shortcut. This would really help you solve most of those problems on molarity that are in the lab manual. So in some cases in a biology laboratory or your chemistry laboratory, it's convenient that you have a solution from which you can take from there of some substance, and you can use it to make lower concentration solutions. So you build yourself up at what we would call a stock solution, and then that stock solution is at a higher concentration, and then you can use it to make lower concentration solutions. So this would be the case right here. Let's say we have an Erlenmeyer flask here, and this is our stock solution. It's some higher concentration, molarity or percent concentration. And we got to take a certain amount in there, and depending on the volume of the diluted solution we want to make, we select the right volumetric flask, and then we got to figure out how much of the stock solution do we put in there that when we make the volume we want, we get the new desired diluted concentration, right? So a key here is to know the concept of stock. The stock solution is the convenient, more concentrated solution you start with. Okay? So here is a typical situation here. Let's say we have a stock solution of sulfuric acid, and in this case, it says that the concentration of sulfuric acid, which actually a real concentrated stock solution would be 18 molar. In this case, this one is only 2.5. You always label your containers with what there is as a safety thing. So it's 2.5 molar sulfuric acid, H2SO4, and we wish to make a diluted solution, it says here, of 1.5. So we want to make a 1.5 molar H2SO4, sulfuric acid solution. And we want to make 600 milliliters of it, right? Okay, so we're talking about our stock and our volumetric. There is a concept equation that's going to help us do this. So we're going to talk about the molarity or the concentration, whatever concentration is in, of our stock or our first solution, and the volume of that. And then that's going to be equal to the molarity that we desire to get and the volume that we want, okay? So think of the right as the diluted numbers and the left as the stock numbers from the stock solution, okay? And so when we read this problem here, we want to identify, well, what are we given here? We're given the molarity of the initial solution, the stock solution. So this was kind of like the equal sign between the stock and the dilution, right? And so when I think about, well, if we rate the stock is with the subscript 1 and the diluted subscript 2, what we get second when we're done, well, what are we given? Well, in this problem here, we're given the initial molarity. It is equal to 2.5. And here we can just keep capital M. We don't need to write as moles per liter. And the volume, guys, you don't have to change it to liters here as long as all volumes are kept in the units that they're in. So if they're in milliliters, just make sure they're all in milliliters. If they're in liters, make sure they're all in liters, and this equation will work. But when you're doing the other calculation we were doing earlier, you have to make sure you're aware of what units of volume you're supposed to be working with. Remember, for molarity, it's liters, right? For percent concentration, it's milliliters. Now, this is asking what volume of this do we need to put in this container, which is a 600 milliliter container? What volume of this do we have to put in there that when we fill this to 600 milliliters, this gives us a 1.5 molar solution, right? So the volume we need to take from the stock, we don't know. That's usually the unknown. I don't know what volume. We need to take a certain volume, and that depends on what concentration we want to make, and how much we want to make of that diluted solution. Okay. So what else is given here? We want to make 600 milliliters of our new solution, the diluted solution. Okay. And again, we can keep those units. And we want it to be at a new molarity or concentration of 1.5 molar. And then all we got to do is use this equation. Okay. We don't know volume 1. We do know the initial molarity of the stock. We know M2 and we know V2. So all we're going to do is substitute into that equation there. 2.5 molar. V1 is the unknown. That's how much we got to put in the stock solution. Okay. And then we're going to plug in. We want a molarity of 1.5 molar. And we want 600 milliliters. Okay. So basically all we got to do is solve for V1, which is how much of the stock solution we want to get. So we're going to divide both sides by 2.5 molar. And this is the reason why we don't have to switch the big M to moles per liter, because the big M cancels right there anyway. If we put moles per liter instead of big M, that would cancel anyway. So now with a calculator, just do the magic there. 1.5 times 600. And then order of operations, right? It's all multiplication division. And then finally, you just divide by 2.5. And that tells us that if we were going to make this 600 milliliters of 1.5, how many milliliters of the stock would we need to get? We would need to get 360 milliliters. So what we would do is we'll get 360 milliliters and put that in there based on our calculation. We put it in there and then we fill it to the line where it's at 600 milliliters, and that's going to give us the concentration we wanted, which was 1.5 molar solution. So that's how we would use this equation. Now there are some practice problems in your lab manual that you're asked to do as one of the tasks this week as well for dilutions. Make sure you do those. There's an answer key that gives you the answers for all the solution problems, so you can check to see if you can get the answer. If you can't get the answer, please get help so that we can make sure you can do these. You'll be expected to do some basic molarity or dilution problems when it comes to both the quiz for this lab and on your major lab exam at midterm. Okay, now, so make sure you reach out to me on those things. And some of the, again, I try to highlight some of the important reasons why we need to go over this. Molarity is important for understanding pH, for example. This one's important because in the laboratory, in real laboratory settings, you're going to be oftentimes having a dilute solution. So all of these things are important on a practical sense. So again, I hope this helps. Reach out to me if you do have any questions.